welcome back. So this is lecture 7 and 8 of probability. And you remember what we did last week. We started looking at continuous random variables. Right? And so what we did is we looked at a few notions for continuous random variables. We looked at the probability density function, right? And we said that if I want to compute a certain probability of x being between A and B, this is essentially this area here. I have here A and I have B, right? Well, I have to define essentially a probability density function, that is this curve here, f(x) of x, right? And if we integrate this PDF between A and B, essentially we get the probability that x is between A and B. Then we looked at CDF, right? That's the cumulative distribution function. So we're looking at the probability that x is smaller or equal to u, essentially. Then we look at expectation of x, right? So the expectation of x is the integral between minus infinity and plus infinity of x multiplied by the PDF of x. And we looked at the variance of x, which is the expectation of the square, this is also called mu, which is the expectation of the square of the deviation between x and its mean. So this is written as the integral between minus infinity and plus infinity of x minus mu square multiplied by the PDF of x. Okay, so what's the main difference with the discrete case is really in the PDF we don't play with probability mass function, we play with probability density function. So the probability mass function was really giving you probabilities for each values of x. Here the PDF is not a probability, it's just a density. So you have to integrate over a certain domain, over a certain interval in order to get a probability. Good, so what we're going to do today, we're going to look at different form of continuous random variables. We'll look at uniform, we're going to look at exponential, we're going to look at the most famous one, the normal, also called Gaussian. We're going to play with those today. So starting with the simplest one, the uniform. So if I have a random variable is continuous and uniformly distributed, and I can call it this way, x is uniformly distributed between A and B, so within an interval A and B, what that means is that I have a probability density function, a PDF, that is flat between the interval A and B and is equal to 0 outside. Right, so for this to be a valid probability density function, what we need is actually this value here should be 1 divided by B minus A, so that the area of this under the curve here is essentially equal to 1. Okay, so what is my probability density function is 1 over B minus A if x is between A and B, and otherwise I have 0. And you can compute the CDF of this. So the CDF of x, right, that's the probability that x is smaller or equal to u. Right, so what do we get? Well, if u is smaller or equal to a, right, obviously the integral will be equal to 0. If u is larger or equal to b, we're going to get 1. And in between, if u is between a and b, what do we get? We get essentially the integral between a and u of 1 divided by minus ba dx, which is u minus a divided by b minus a. Okay, so indeed, if you plot this, you plot this CDF, right, at a and b, you have here that is something that is equal to 0. You have here at b, you have something that is equal to 1, right? So this is 1. and in between you have a linear increase. The CDF linearly increase with U, essentially, between A and B. Okay, I think nothing, no major difficulty here. You can compute the expectation of x, right? That's the integral between minus infinity and plus infinity of x, fx of x dx, right? So here, in this case, is the integral between a and b of x divided by b minus a dx. And if you do this, what you get b plus a over 2, which is quite natural. Essentially, you have something that is uniformly distributed, so your mean is here at a plus b over 2. Right? You can do this at home, no major difficulties. Similarly, you can compute the variance of x. The variance of x is expectation of x squared minus the square of the expectation, right? This we know already. This is p plus a over 2. So what is missing is to compute expectation of x squared, which is the integral between a and b of x squared divided by b minus a dx. And this one, again, you can do this at home, and what you get is b minus a squared over 12. And so what it means is that if you have two distributions, I have a and b here, or I have something where actually I have a and b much further away. Here I have essentially that the PDF is much more spread out. This one is a bit more concentrated, right? So the variance of this distribution here will be larger than this one because the difference between b and a is essentially larger, right? So you have a larger spread around its mean, right? In the second case here, in the second case here compared to this one, because actually you spread the distribution more along this x-axis. Okay, so I think here shouldn't be any major issue. More interesting distribution is exponential. So this is now a random variable that is exponentially distributed. And how do we write this? We say x, typically there are multiple ways of writing this, but one way of doing it is saying this is exponentially distributed, expo with a certain parameter lambda that is positive. And so if we have an exponentially distributed random variable, what it means is actually that the PDF of that random variable is given by lambda multiplied by exponential lambda x for x positive, and if x is negative, it's actually equal to 0. So what we have here is a PDF that looks like something like this, that is decreasing with x, right? And as you increase lambda, essentially it decreases faster. Right? So as lambda increases, you have the distribution, actually the PDF is actually decreasing faster, so you have a concentration that is more towards lower values of x. Right, so what about the CDF of this exponential random variable? Well, that's the probability that x is smaller or equal to u, right? So if u is negative, this will be equal to 0, right? Because here you have the PDF is equal to 0. And if u is positive, what do we get is the integral between 0 and u of this lambda e minus lambda x dx. Right, and this is minus e minus lambda x between 0 and u. And so this is 1 minus e minus lambda mu. Right, so in this case, what do you see is that the CDF, this is the PDF, you have the CDF of this random variable. For large value of u, this reach 1, so you get something that goes like this, right? And if your lambda increases, essentially you get something that increases faster. And for large value of u, you tend towards 1, so as lambda increases. Okay? So this exponential distribution comes from the presence of this term here. So where do we use this? We'll see this in a moment, but actually this is used to model, for instance, components that do not age. So I will explain this in a minute. But more interestingly, in EE, an example in communication is when you have a transmitter and you have a receiver. Again, you have seen this a few times. You have noise here in your receiver, but you have here, you have typically when you transmit a radio wave from a transmitter to a receiver, what you get is multiple echoes of your transmitted signals, right? So you transmit from here to someone in the audience. Actually, the radio waves will reflect on the walls, right? They will actually interact constructively or destructively at the receiver. And so what's happening is actually the power at the receiver will fluctuate. If you move just a little bit by half a wavelength, the received power will be completely different, right? So how do we model this? Rather than actually doing an electromagnetic modeling of all those radio waves, we model this using probability. And so this probability exponential distribution is used to model the distribution of the received power, for instance, in the communication systems, right? So this is a major problem because if you're here and you move just half a wavelength, you may lose maybe 10, 20 dB of received power, right? So your signal is suddenly divided by, your received power is divided by a factor of 10, factor of 100. And actually from a communication perspective, you can imagine actually this actually leads to very significant challenges. Because if you're here, you receive well. If you're there, you don't receive well. So you have to find coding strategy that enables you to recover information efficiently. Right, so how we do this, you see that you have a noise source there. That noise will actually induce will corrupt the signals. But also on top of this, you have your received signal will fluctuate very, very dynamically. Right, so you have two sources of randomness here in this example. Right, so if you take a fourth-year course on comms, then you will see this extensively, how we actually model this and how we design coding structure or communication strategy that actually very robust to this kind of situation. Good, so this is obviously a valid probability density function, right? This is positive or equal to 0, right? You can also compute that the integral between 0 and positive infinity of lambda e minus lambda x dx. This is equal to 1, so that's a valid PDF. Okay, so one more thing. This exponential distribution has something that is it has an interesting property that is called memoryless property of the exponential distribution, and it says the following: if I have a random variable t that is exponentially distributed with parameter lambda, if I compute the following, the probability that t is larger than a plus b, given that t is larger than a. Right, so what that means, t, for instance, can be the lifetime of something, lifetime of a component. So you're looking at components, electronic components, and you say, well, this component functions a unit of time, and what you're interested is to calculate the probability that actually will compute an additional b unit of time. Right? So this is probability of having t larger than a plus b, intersection that t is larger than a, divided by probability that t is larger than a. Right? We have done this. What is this? This interval is smaller than this one, is included in this one, so this is a probability that t is larger than a plus b, divided by probability that t is larger than a. Okay? So what is probability that t is larger than a? This is 1 minus the probability that t is smaller than a. Right? So this is 1 minus f of t evaluated at a. This is 1 minus what we have here. Right? That's the CDF of x evaluated at u. So that's what I'm doing here. I'm evaluating the CDF of t evaluated at a. So it's 1 minus exponential minus lambda a. Right? So this gives you exponential of minus lambda a. Is that clear? Right, so what do we get with this? We plug this into here. P of t larger than a plus b. Rather than having a, I have a plus b. So I'm going to have exponential of minus lambda a plus b divided by exponential of minus lambda a. And this is the same as e minus lambda b. Right, so you get here a conditional probability that is not a function of A. It is not a function of A, right? It's only a function of B. This is the same as the probability that T is larger than B, right? Probability that T is larger than B, you replace A by B and you get this. So what you see here, you're looking at the lifetime of components. You know that actually it functions properly A unit of time. You wonder what's the probability that actually it functions an additional B unit of time, given that it has functioned A unit of time. And this is just the probability that it functioned B unit of time. So it's a memory-less property because it's not a function of A. It's not a function of how long this component has already worked, right? So can this distribution be used to model the lifetime of the human population? No, it cannot, simply because if you are 80 years old and you're looking at the probability of actually living an additional 10 years, that probability will not be the same as if you are 10 years old and you're looking at the probability of living till you're 20, right? So you see, this is a case where actually this memoryless property really applies to some specific behavior. It cannot be used to model anything. So the lifetime of human population is not something, of a human being is not something that will be modeled using an exponential distribution, but it can be used to actually model some form of, often for electronic components. It's not a function of how much it has actually worked properly. It's a function of how long actually it's going to work. Good. So we will come back to that later on when we're going to look at different ways of looking at this memoryless property. But just keep this in mind. So we have PDF, we have CDF. What can we compute? We can compute the expectation, right? So what is the expectation of this exponential random variable is expectation of x, right? And what we do expect from here, we see that as lambda increases, essentially that distribution is shifted more towards lower values of x, right? So you see that you expect that as lambda increases, essentially the mean of that distribution will shift towards lower values, right? So how can we compute this? Well, again, that's the definition. X multiplies by fx of x dx. Right, exponential random variable is always positive, so this is the integral between 0 and infinity of x lambda e minus lambda x dx. So 2 years ago, you came here for the interviews, admission interviews, right? Any one of you had interview with me? No? Okay, surprising, right? So this is a question that actually I ask, right, to compute this. I'm sure you can all do this by now, but so how do you compute this? You use simply integration by part, right? So I think this is something that you should all be familiar, right? So u is x, dv is lambda e lambda x dx, du is dx, and v is minus lambda x, right? So once we have this, we can compute this integral. That's uv, that's x, multiplied by e minus lambda x dx, 0 plus infinity, minus v du is minus and minus, that's plus e minus lambda x dx. What is this? That's 0. Right? If you cannot do this, you can apply L'Hopital rule. Right? I'm sure now you're all familiar with this. You can do that, right? So I'm saying this because a few years ago, I think I had 80% of the students could not do it. Right? What is this? right? So the first term will be 0. The second term will be 1 over lambda, right? So you get indeed that expectation of x is 1 over lambda, right? As you increase lambda, the mean of that PDF will move towards lower values. Okay, let's look at the variance. Right, so variance of x is expectation of x squared minus the square of the expectation. This one we know already, right? This is 1 over lambda. What is expectation of x squared? So again, this is integral 0 plus infinity of x squared lambda e minus lambda x dx. Right, and so what we can do here, we can use integration by part again. So I take u is x squared, dv is lambda e minus lambda x dx, du is 2x dx, and v is minus lambda x. Right, so this gives me uv x squared minus multiplied by e minus lambda x between 0 and infinity, minus integral 0 plus infinity of v du. I have a minus here, plus the minus there, that's plus e minus lambda x multiplied by 2x dx. What is that? That's still 0, right? Again, you can do L'Hopital if you want, and you can do it twice. You can apply twice L'Hopital, right? Now, what about this one? This one is, let me write this differently. This is 2 multiplied by integral of this, x e minus lambda x dx. And if I multiply by lambda here, I divide by lambda there. Right? So what is this? That's e of x. And so we just did it. This is 1 over lambda. Right? So this term is 2 divided by lambda squared. And so you bring this into here. You have 2 divided by lambda squared minus 1 over lambda squared. This is 1 over lambda squared. Right? So indeed, as you increase lambda, here in that distribution here, as you increase lambda, you see you're really shifting towards lower values, but also the decrease becomes sharper, so actually the distribution becomes more centered around its mean, essentially. That's what this means. You have less deviation around its mean. Okay? So make sure actually you can use L'Hopital and you can compute the limit. This is very important. In some exam questions, sometimes you have to do that. Okay, so let's move on to another problem. Let's imagine now that I have a random variable x, and what I know this probability density function of x, and what I'm interested in is a random variable y that is a function of x. And what I'm interested in is what is the PDF of y. Okay, so I know the PDF of x. I know that actually I have a certain function of x. And what I want to do is to have the PDF of this new random variable y. So let's look at an example to see how this works. So let's imagine that I have x is exponentially distributed with parameter lambda. And I'm looking at y is equal to cx. So I just multiply by c. Right? And I start with here c is positive. Okay, so let's calculate this. How can we calculate the probability, the PDF of y? I can first compute the CDF of y. We see the probability that y is smaller or equal to y. This is the probability that cx is smaller or equal to y. That's the probability of x being smaller or equal to y over c. This is the CDF of x evaluated at y over c. Right? How do we get the PDF from the CDF? Assuming actually the derivative exists, I can take the derivative of that CDF. And what do we get here? Well, we get a composite function. We get the derivative of this, that's the PDF of x evaluated y over c, multiplied by the derivative of the argument, which is 1 over c. Right, so what do we have here is when you replace this by the PDF of x, which is 1 over lambda multiplied by e minus lambda x, right, for x positive and otherwise is 0, what do we get here? We get that lambda multiplied by e minus lambda x. Now the argument is y over c, so I have y over c multiplied by 1 over c, and this is when y is positive and otherwise is 0. Okay, so what you see here, if I write this differently, is y over c multiplied by e multiplied by y over c. Lambda over c, exponential of minus lambda over c multiplied by y for y positive, and otherwise it's 0. Right, so what you have here, if you like, this is a lambda prime. And so you know that lambda, that y, this new random variable y, is, what is the distribution? That's right. So this is still exponentially distributed, but now with a parameter, not lambda, but lambda over c, right? So in this case, if c is positive, I take an exponentially redistributed random variable x, I multiply by c, what I get is still exponentially distributed, but the parameter is not lambda, it's actually been divided by c. Right, so this is an example. What I did here, the process here is very standard. What you do, you start with finding the CDF of y, and you try to express this as a function of the CDF of x. Then you take the derivative of this, and you write this as a function of the PDF of x. Okay? So let's look at the other case. So what if c is not positive, but rather is negative? So I have second case, y is cx, and c is negative. But I can still do the same thing. I can still write this. It's probability of y being smaller than y. This is the probability of cx being smaller than y. So let's introduce, now c is negative. So let's introduce d, that is minus c. Right, so d is now positive. Right, so this is probability of having minus d, x being smaller than y. This is the same as having the probability of dx being larger than minus y. This is the probability of having x being larger than minus y over d. And so how can we express this? What I'm looking at here is the following. I have a certain values here. I have a certain distribution. I'm not looking at this probability here, but I'm looking at the complement. I'm looking at this one, the probability that x is larger than something. So this is the same as 1 minus the probability that the x is smaller or equal to minus y over d. Okay, I'm looking at the complement. I'm looking at this probability, and I'm writing this as 1, which is the area under this curve, minus this area. Okay, so now that's good. I can take a derivative of this. So fy is now the derivative of the CDF with respect to y, right? Now, when I take the derivative with respect to 1, that's gone. So I'm going to have the derivative, and this is 1 minus f of x evaluated at minus y over d. Right, so I'm going to have the derivative of this quantity, that I'm going to have minus the PDF of x evaluated at minus y over d, multiply by the derivative of this with respect to y. This is minus 1 over d. Good, so let's plug now this PDF. So again, if I if I write fx of x is lambda e minus lambda x, for x positive and then otherwise is 0, what do we get for fy of y? Is minus and minus here. Those two cancel each other, right? So I can discard this, but I have 1 over d multiplied by lambda e minus lambda plus y over d. Okay? And what is y now? Y is negative, right? Y is negative because c is negative, so this quantity is always negative, right? It has to be negative. If y is positive, you get 0. Right? If I write this as a function of c rather than d, I have minus lambda over c e minus lambda y over c. And this is for y negative, and for y positive, I have 0. Okay? This part is a bit more difficult than the previous one, but it's using the same principle. You start with the CDF, you write this as a function of the CDF of y, you write this as a function of the CDF of x, then you take a derivative of y, and you write this as a function of the PDF of x. Right? Now, if you compare those two, if you compare what you have here, you can see the two. You have this one here, right? And you have this one here, right? The difference between this and this is just that I have a minus here, right? So in general, the solution here, whether you have c is positive or negative, what you write is lambda over c. You take the absolute value, exponential minus lambda y over c. So this is what you can see, and this is actually the form that you can obtain if you actually compute this PDF more generally. If you have x, you do a transformation of g of x to get to y, right? If this g of x has some property that is actually either increasing or decreasing, so this is what we call a monotonic function. So it's a function that actually is either increasing or decreasing. So this is what we had here. C would have an increasing function, positive. C negative would have a decreasing function. Then what you can do, you can write that the PDF of y is equal to the PDF of x multiplied by something in the absolute value here is the derivative of x with respect to the derivative of y. And so what we did here, this quantity is actually this term here, and this quantity here is actually this term here. We had y is equal to cx, right? So x is equal to y over c. And so what you do here is actually you take the derivative of x with respect to y, and that's why you get this 1 over c that comes in. Okay, so this is actually an expression that you can use. If you have monotonic function, is an expression that you can use. I find it usually easier to actually do the development I just did earlier. I think it's more intuitive because you really start from the PDF, the CDF. You express this CDF of y as a function of CDF of x, and then you take the derivative. These steps always works, and we're going to use this later on today as well. But this is also something good, so this is also something that you can apply. Okay, so where can we use this? Well, we can use this when we look at Gaussian distribution or normal distribution. So when I have a normal distribution, and this is probably the most well-known distribution, right? I have x is normal distributed with parameter mu and sigma square. What is mu? Mu is actually the expectation of x, and sigma square is the variance of x. And we're going to see this in a minute. We're going to show this. So what is this? What is the PDF of of a normal random variable is given by this. Very well-known expression that you may have seen in your A level. It says the following, and this has actually a certain shape. It has this kind of bell shape, very symmetric shape, right? That is centered around mu, right? That's the mean, and it has a certain variance, sigma square, right? As you move mu to higher value, your distribution is shifted to the right, essentially. As you increase sigma square, the deviation around its mean changes. So I can have something that looks like this, or I can have something that looks, for instance, like this. Right? So the red one would have actually a variance that is larger than the blue one. Okay, so this is actually the PDF of a normal random variable, mean mu and variance sigma square. Now what if I take the mu equal to 0 and the variance sigma square equal to 1? So this is often called standard normal, and we're going to denote this by z, like n01, has a 0 mean and has a variance of 1. So now I have something that is like this. I have the mean around 0, so I have my bell shape is actually centered around 0, and I have a variance that is being normalized to 1. So the deviation around its mean has been normalized to 1. Okay? We'll see the standard normal is very helpful because a lot of computation actually based on this, and then we can translate it to some x if the mean is non-zero or the variance is not equal to 1. So the first question we can ask ourselves once we have defined this, and let me write f of z, right? So that's the PDF of the standard normal random variable is now simply 1 over square root of 2 pi e minus z square over 2 over 2, because sigma square is equal to 1, right? Good. So first question, is that a valid PDF? So what do we need to show to, what do we need to do to show that actually this is a valid PDF? I need to show that the integral of this quantity between minus infinity and plus infinity is equal to 1. So if I write this, this is 1 over 2 pi square root between minus infinity and plus infinity of e minus z square over 2 dz, and this has to be equal to 1. Right? This is what we have to show. Or in other words, I can say integral between minus infinity and plus infinity of 1 over 2 of e minus z square over the 2 dz is square root of 2 pi. Okay, so let's try to show this. And to show this, I will write this as I. This is my integral I want to compute. And I can write I as something slightly different. You know that here, what is the property of Gaussian random variable? That is that the PDF is symmetric, right? With respect to 0, the positive part and the negative part is perfectly symmetric, right? And why it comes? It comes from the fact that you have this square here. Right? So the positive and the negative actually are perfectly symmetric. That means actually I can compute this as 2 times the integral between 0 and positive infinity of e minus z square over 2 dz. Right? So what I'm saying here is actually this integral here. So the part in red and the part in blue are the same. Okay, and this is another integral, this is j. So let's compute j. But rather than computing j, I will compute j squared. And you will see why. This is actually a complicated integral to calculate. So rather than computing this, I will compute j squared. And I will just make a change of variables here. I will call it x squared over 2 dx, multiplied by 0 plus infinity minus square over 2 dy, right? So this is j, this is still j, right? So this is j squared, right? I'm just having 2 different integration variables, but that does not change anything, right? Now why do I do this? Because if I do that, what you can write is something simpler. You can say j square is a double integral, no? Of e minus x squared plus y squared over 2 multiplied by dx dy. Is that something familiar? How do we solve this? We can go from Cartesian coordinates to polar coordinates. Have you done this? Yeah. Good. So what I can do here, I can go from Cartesian to polar coordinates, and I can make a change of variables and say x is r cos theta, y is r sine theta. And now I have this quantity dx dy will be the determinant of some Jacobian multiplied by dr d theta. What is this j? It's a matrix that is given by the derivative of x with respect to r, the derivative of x with respect to theta, derivative of y with respect to r, derivative of y with respect to theta. And so if you compute this, what you get here, dx dr is cos theta, dx d theta is minus r sine theta, dy dr is sine theta, dy d theta is r cosine theta. Right, so the determinant of j is now equal to r. So what you have here is r dr d theta. And so rather than looking at the Cartesian coordinate, if I have this little square here of dx dy, now I'm looking at this differently. I'm looking at this using polar coordinates, and now I have something that looks like this. Right, this is r, and this length here is r d theta. Right, this is a certain angle here that I have d theta. Right, so if I do this, now I have j square is, I replace x and y by r and theta. Right, so I'm looking at x is positive and y is positive. So I'm looking at this quadrant here where x and y are positive. So r has to go from 0 to infinity, and theta has to go from 0 to pi over 2. Right? So I'm integrating between 0 and plus infinity, between 0 and pi over 2. Exponential of minus x squared plus y squared. Right? This is equal to r squared. Right? R squared cosine squared theta plus r squared sine squared theta, this is the same as r squared. So I have r squared over 2 multiplied by dx d theta, that's equal to this. That's r dr d theta. Okay? D. Yes, you can change the ordering. Yes, so I will do it now. So you can integrate like this. Right, and you can compute this integral first, and then you can compute d theta. So this just change of dr d theta. Right, so this is actually much simpler to compute because you have the presence of this r here. Right. So what we can do is compute this, and so what do we get here is minus e minus r squared over 2 between 0 and infinity, right? This quantity, and this is essentially equal to 1. So what I'm left with is integral of 0 to pi over 2 of d theta, and this is equal to pi over 2. Right, so we have j squared is pi over 2. And what we had here is I is equal to 2j. I is equal to 2j. So it's equal to 2 multiplied by the square root of pi over 2 that's essentially equal to square root of 2 pi, and then we get indeed what we were expecting. Okay? I think this is something that you have done, probably in calculus, or this is just a proof. Actually, I was told, actually, if you go to financial engineering or in the city and you want to do math for finance, they may ask you that question to prove that actually the normal distribution is a valid, the normal PDF is a valid PDF. I don't know whether it's true or not, but that's what I was told by some people in finance. Good. So, interesting, but how do we use all those stuff? So, let's first compute expectation of z. So we have z. How can we compute the expectation of z? We said already earlier on that if you have a standard normal random variable, the mean is 0. So we should be able to show this, right? Expectation of z is the integral between minus infinity and plus infinity of z multiplied by the PDF of the standard normal random variable minus z squared over 2 dz. You can compute this at home, and what you get is equal to 0, and the reason is because this integral, the function you integrate here, is an odd function. So you have this quantity here that will, the z that will be negative if z is negative, positive if z is positive, and the two will cancel each other. Right? If you have expectation of z squared, right? Where can you use this to compute the variance of z? So you compute the variance expectation of z squared minus the square of the expectation. This is equal to 0. This one needs to be computed if you want to compute the variance. So expectation of z squared here again, you can do this, is integral between minus infinity and plus infinity, z squared 1 over 2 pi e minus z squared over 2 dz. And you can do this using integration by part. You can do this at home again, right? There is no major difficulty. It's just classical integration by part. And what you get is actually expectation of z squared is equal to 1. And so the variance of z is indeed equal to 1. Okay, so this can be shown simply by computing this expectation using integration by parts. So this is about z, but z, again, is normal with mean 0, variance equal to 1. What if you have x is equal to mu z plus mu? Right. So if we write x as mu z, rho z, sigma z plus mu, so I take a standard normal random variable, I multiply by the standard deviation, and I add the mean. What do we get? Right? So what is the PDF of x? Right? So how can we do this? Again, I can start with the CDF of x and say this is, I can replace here. So I have, again, a change of random variable. This is the probability of z being smaller than x minus mu over sigma. This is the probability, the cumulative distribution function of z evaluated at x minus mu over sigma. Right? So what is fz of u is, again, the integral between minus infinity and u of the CDF, of the PDF of the standard normal random variable. Right? Now I have this. This is the CDF of x, evaluated at x. What I'm interested in is the CDF, the PDF of x. So I can take the derivative of the CDF of x with respect to x. So I can take the derivative of this with respect to x. And what do I get is the PDF of that standard normal random variable, but evaluated at x minus mu over sigma, multiplied by the derivative of this argument with respect to x. So this is 1 over sigma. And so what do we get? Is f of z is this argument here, right? So I have 1 over 2 pi, take the square root, E minus what? Z squared. Z squared becomes this. X minus mu square over 2 sigma square, with the sigma coming from there. Multiplied by 1 over sigma, this is 1 over 2 pi sigma square, E minus X minus mu square, sigma square. What is that? That's the PDF of what? If you compare to what you had here. Right, so if you compare those two, that was a definition of the PDF of a normal random variable. Right, if you compare this to this, it's the same. It's the same. So that means actually this is actually normal distributed with mean mu and variance sigma squared. So what does that mean here? What did we do? What we did is we said Z is standard normal. I have a mean 0 and variance of 1, right? And I create a new random variable x by simply multiplying Z by sigma and adding mu. So by doing this, what I did is I have a Z that is normal, standard normal, mean 0 and 1. And I take a transformation that is sigma Z plus mu. This is my x. And I have now a new random variable x that is normal distributed with mean mu and variance sigma square. Okay? Essentially what we did is a change of random variable, right? We changed the variable from Z to x. Z was normal distributed, standard normal 0, 1, right? And by doing this simple linear transformation here, we get a new random variable that has a different, is still normal distributed, but has a different mean and a different variance. The mean now becomes mu, and the variance becomes sigma squared. Right? So this operation is really important. This is something you're going to do extensively. It helps you, it enables you to go from a standard normal random variable to something that is non-standard, that has a non-zero mean or have a variance that is not equal to 1. Okay, is that clear? Right, that's a very important step, obviously. Okay, so once we have that, we can compute expectation of x and variance of x. So what is the expectation of x? So if x is normal with mean mu and variance sigma square, expectation of x is this whole thing. X multiplied by 1 over 2 pi sigma square E minus x minus mu square divided by 2 sigma square dx. And you can compute that. And if you compute that, it's a lengthy process, but you're going to get mu. Right? So this is the first way of computing this expectation. You take the definition of x, the expectation of x is the integral of x multiplied by its PDF, and you compute essentially that integral. Another way of calculating expectation of x is simply by saying this is expectation here of sigma z plus mu, right? Because we have this relationship here, right? So I can simply do this. And you remember what we did last week. We had this, and we said this is the same as a expectation x plus b. So this is the same as sigma expectation z plus mu. Expectation z is 0, so this is equal to mu, right? So those are two different ways of computing the expectation. Here I'm relying on the fact that indeed you can write x with normal random variable with 2 parameters here as a function of a standard normal random variable with z is normal 0, 1, right? You can use this relationship, and from there you can compute the mean. Or you can actually directly compute this integral. But in this case, this is much easier to compute. And similarly, if you look at the variance of x, right, and you want to show that the variance of x is indeed equal to sigma square, you can do that. You could actually compute the integral and apply the definition. So you could say this is this quantity x minus mu square multiplied by the PDF of x dx, right? And if you compute this, you get sigma square. But a simpler way would say this is the variance of sigma z plus mu. And what we have done last week, we said variance of ax plus b, what is it equal to? A square variance of x, right? So if you apply this to here, you get sigma square variance of z. Variance of z is equal to 1. You get sigma square. Okay, so this relationship is actually very, very useful. It really enables you to go from standard normal random variable to something that is non-standard. Okay, so let's have a break here, 5 minutes, and then we're going to continue and see how we can compute the CDF of normal random variables. So this is an example of what it looks like. So when you draw those PDF of the Gaussian or the normal, I mean, you see people call it normal, people call it Gaussian. So this is an example of what you had. This is a standard normal random variable, or the PDF of the standard normal random variable, mean 0, standard deviation of 1, or variance equal to 1. This is what's happening when actually you increase sigma from 1 to 9. So you see actually the distribution becomes fatter, if you like, right? It's spread around this x-axis here, so it's actually the deviation around its mean actually becomes larger. Here, if you take mu equal to 2, you take this and you shift it by 2, right? And here is when you change the mean and you change the variance, essentially, right? So this is a standard normal random variable. Those ones are not standard, right? They have either the mean is non-zero or the variance is not equal to 1. Okay, so an important question is how do we compute the CDF of a normal random variable? So let's start with standard normal random variable, mean 0 and variance equal to 1. And I'm interested in the probability that z is, for instance, smaller or equal to 0.5. Right? So what is this? This is the integral between minus infinity and 0.5 of 1 over 2 pi square root e minus x, or e minus z square over 2 dz. Right? This integral, you cannot compute it in closed form. There is no solution for this. You can compute it numerically, and this is what you have there, or you can use tables. And so this is an example of what this does, essentially, is to compute the CDF of a standard normal random variable. What you have here is the value of z that is positive. So, for example, you have 1.0. If you take the row here, you're going to have 1.0, 1.01, 1.02, and so on. And that value here is actually the CDF. So if I'm looking at this, 0.5, I'm looking at here, z is equal to 0.5, I will have a value that is 0.6915. Right? This is 0.6915. So what that means is that I have the standard normal random variable, the PDF, with mean 0. I'm looking here at 0.5, and what I'm computing is this area here. Right? So this is, you use table to do this. In MATLAB, you have a function that does this as well. There is no closed form solution. This is one of those really distribution that do not have closed form solution, but you can actually evaluate this numerically, and this is the outcome of those. So in the notes, at the exams, what you have is that you have a formula sheet where you have the following. You have this. And actually, this is the same as as what we had in the previous table. You have here values of y that are positive. You have here the PDF of this Gaussian standard normal random variable, and this is the CDF. So with y is equal to 0, the CDF is equal to 0.5 because it's symmetric around 0, right? So if your value is you're looking at 0, the CDF is this part is equal to 0.5, right? So the content here is actually the same. If you look at 0.5, right, you are here, you had 0.691, which is the same as what we had here. So what you have on this table and this table is essentially the same thing. The only difference that you have the additional column here, the second one, that is the PDF, but the third one, the CDF, is the same as what you have here, but here is a bit more detailed. Right, so what you have in the formula sheet in the exams is actually this table. Okay? Good. So what you note here is that this holds for values of, so this holds only for standard normal random variable, right? This is only for z that actually is normal distributed with 0 mean and variance equal to 1. But you know that actually those values of z's here are positive. So what if you're looking at the probability of z being smaller than minus 0.5, for instance, right? So this quantity now is negative. So what you have is that you have 0, you have minus 0.5, you have the distribution like this, and you're looking at this integral. Right? So what we use here, we use the symmetry of the distribution. And we're saying that this quantity, this area, is actually the same as this area, where this is 0.5. So the blue one and the red one are the same because of the symmetry around 0. Right? So what I can say here, this area is actually the same as the probability 1 minus this area is the same as this area, and this area is 1, which is the area under the curve, minus this part. So this is z smaller or equal to 0.5, right? So z equal to 0.5 is this whole area here. 1 minus this whole area is the red part. The red part is equal to the blue part. Is that clear? Right? So now you can do that. This is something that you have. This is this quantity 0.615, and so you can compute the probability that z is smaller than minus 0.5. Okay? So in general, when you have something negative, you can always write f of z evaluated at minus z plus f of z at plus z is actually equal to 1. Right? This holds for this normal random variable simply because of the symmetry of the distribution. Okay? Good. So what if I have another example to compute probability? So if I have now probability of z, I have still a standard normal random variable, but I'm looking at the probability of z that is between minus 2 and 1. So I have this, I have minus 2 here, and I have 1 here. I have this distribution like this, and I'm looking at this area, right? So this is the probability of z, or the CDF of z at 1, right, minus the CDF of z at minus 2. So what I'm looking at is the CDF of z at 1, all this, minus the CDF at minus 2, this, simply. Right? So this is simple. What you do here, fz of z of 1, you can find it there. So this is fz of 1, minus fz of minus 2. So you use this relationship that we had here. So that's going to be minus 1 minus fz at 2, right? So this is fz at 2, right? So here you have fz at 1 minus 1 plus fz at 2. And so you can compute those quantities here again. You look at the table. Fz of 1 is here somewhere, right? 0.84. right? So this is 0.84. Fz at 2 is up there, 0.97, right? And by doing this, you actually compute the probability of having the standard normal random variable within that interval. Okay? That shouldn't be too complicated, but keep in mind that actually this holds only for standard normal random variables. So you cannot do this if the mean is non-zero or the variance is not equal to 1. Right? In that case, you cannot use the table as it is. What you have to do, and before we go into this, one more thing I want to show you is what's happening if you're looking at the probability of having z between minus 3 and 3. So this is, again, using the relationship we had here. This is fz at 3 minus fz at minus 3. This is fz at 3 minus 1 minus fz at 3. Right? So this is 2 fz at 3 minus 1. And fz at 3 is here 0.9987. 0.9987. So what you see here, this is actually a very large number, 0.99 something, right? So what that means is actually when you have z is standard normal random variable, and you look at the distribution like this, and what you're looking at is the integral between minus 3 and 3, this probability is almost equal to 1. So this is actually what is called the 3 sigma rule. If you have a normal random variable and you take anything between minus 3 and 3, you have very high chance actually of having the values will fall within that interval. Right? So the probability of having z between minus 3 and 3 is almost equal to 1. You have a very low probability of having being in the tail there. Right, so we're going to go back to this in a minute when we look at x, but this is actually useful to have in mind, that you have relatively low probability of having small values here and large values there. Good, so this is all about z, but what's happening now if you have x that is normal random variable mu sigma square, and now you want to compute fx of u, right, which is the probability of x being small or equal to u, right? So what do we do there, right? We don't have a table. We have the table only for standard normal. So what we have to do, we have to standardize this random variable, and so what we say is that we write x as sigma z plus mu. So this is sigma z plus mu being smaller or equal to u. This is probability that z is smaller or equal to u minus mu divided by sigma, right? And so the probability of x being smaller than u can be actually computed as a function of the CDF of z, the standard normal random variable, and evaluated at a certain value, u minus mu divided by sigma. Okay, so let's look at an example of this. Imagine that x is normal distributed, mean 3 and variance sigma 5 square. So the standard deviation is equal to 5. And you're looking at the probability that x is smaller or equal to 5. So what you can say is that this is the probability of having sigma z plus mu being smaller than 5. What is sigma here? It will be 5. What is mu? It will be 3. This is probability of z being smaller than 5 minus 3 divided by 5. This probability of z being smaller than 0.4, right? And so you can compute this quantity here, 0.4 again. Right, you go there, and you get 0.65, right? So this is the probability that x would be smaller than 5, right? So do not apply this directly to a standard, to a normal random variable that is not standard. You have to standardize it first, right? And standardizing first means essentially what we did here. You can always write z as x minus mu over sigma, and this is what we did here, essentially. Yes?
Any other
The other column is actually if you want to have more accuracy. So if you're looking at z is smaller than 1.005, for instance, right? So you have z is smaller than, I don't know, 1.01, for instance, right? Then you go into the second column. 1.01 would be here, right? You're going to have all the way to 1.09, right? You have, that's the only difference. So which is something that you don't have in this expression here. You have only one digit after the comma here, right? And here you have some specific values of y and some corresponding values of the CDF. Okay, with this, I think we're done with the normal random variable. I hope you grasp this concept. It's actually quite fundamental. You're going to use this extensively. And where is it used? One of the case where actually is used a lot when you have a communication is the example I gave earlier. Here, this noise here is actually very often modeled using a normal random variable. Because of the contribution from all the terminal nodes, all those electrons moving, essentially you can show that actually this behaves as something that is normal distributed. So here you have something that is typically normal. In the communication systems, the information, the way it's transmitted, you have normal distribution that comes in as well. So there you have some random variable that is normal. There you have something that is normal. Here, the channels here, you have something that is exponentially distributed. And then if you model the packets arriving here, you have this Poisson distribution we looked at last week or 2 weeks ago, right? So this is just an example where you already have multiple random variables that come together into the design of the system. Good, so with this, let's move on and let's make use of this to look at slightly more complicated distribution is something that is called chi-square. So if I have a random variable that is chi-square distributed, what that means is the following. I have a standard normal random variable, mean 0, variance equal to 1, and what I'm looking at is another random variable u that is the square of z. Right? I'm looking at a new random variable u that is the square of a standard normal random variable. Right? So this u is actually chi-square distributed. So what is the PDF of this? Well, you see that actually what you see here, you have a function that is not monotonic. It decreases and increases. So what you had earlier on in the expression I showed you when we do the change of variable, right, here, this one you cannot apply it directly because you have a function that is not monotonic. It decreases and increases, right? So in this case, we cannot apply this directly. There is a more general expression that we can use. We'll not go into this. You may see this in the 4th year. What I want to show you is how you can still compute it just using the principle that we have used so far. So I start again as what I have done before. We start with the PDF, the CDF of u. So this is a probability that u is smaller or equal to u. This is the probability that z squared is smaller or equal to u. Right? Now, obviously, this is, if u is negative, even equal to 0, this quantity is actually 0. If u is positive, then what do we have is the probability of having z is contained between minus square root of u and square root of u. Okay, so how can we compute that? Probability of z between minus u and u, this is the integral between minus square root of u, square root here, and square root of u of the PDF of z, which is 1 over 2 pi square root e minus z squared over 2 dz, right? And now what I'm looking at is the PDF of u. So I take a derivative with respect to u of this CDF. right? So I'm looking at the derivative with respect to u of this integral where I have two boundaries here that are both function of u. Right, so how do we do this? We use a theorem that is called, and we're going to come back to it later on as well, is called Leibniz differentiation theorem. And so what this theorem tells us is that if you have a derivative with respect to u of an integral that is a function of z, but where the boundaries here are functions of u, and this is really what we have here, then how can we solve this? We can say this is that function evaluated at this boundary, so is that function here evaluated at b of u, multiplied by the derivative of the boundary with respect to u, minus the function evaluated at a of u, multiplied by the derivative of a with respect to u. Right? And so if you have a of u is a constant, you get only this term. And this is something that we have done before. Essentially, you take that function you evaluate at the boundary plus the derivation of this, you differentiate this boundary. Here is a bit more complicated because both of them, you see here, this is essentially b of u, and this is a of u. Right? So what we can do is apply that theorem to solve that problem. And so what do we get here is the PDF of u. I'm applying this to this case. So first let's first take the derivative of b with respect to u, the derivative of this. So this is 1/2 u minus 1/2. Multiply by f evaluated at b of u. So this is 1/2 pi, square root, e minus z square, and I replace z by square root of u. That's going to be u divided by 2. Minus this one first, so I take the derivative of this. I get minus 1/2 u minus 1/2 here, multiply by this argument evaluated at a of u. That's 1/square root of 2 pi e minus z square. The z is now minus square root of u, so that's u divided by 2, and that's it. Right, so this minus and minus, that becomes a plus. And so what I have here is 1/u, square root of u, 1/square root of 2 pi e minus u over 2. Right? And this holds if u is positive, so this is u positive, and if u is negative, you get 0. Right? That's the PDF on now a chi-square random variable. Okay, so what is really important, you have to be able to do those derivation and show this. Essentially what we do this, again, is the same trick as what we have done before. I start with the CDF of u, I write it as a function of essentially something that is a function of the CDF of the other random variables. And then I take the derivative of this new random variable, and this will be written as a function of the derivative of this one, which is essentially the derivative of the PDF of the of z. Okay? So where is that used? This is used a lot. If you take systems like in communication nowadays, if you take 5G, for instance, even 4G, you have systems with multiple antennas. So you have transmitters and receivers that have multiple antennas. So in your phone, for instance, you may have multiple antennas. At the base station, those ugly towers, you have also multiple antennas. So what we do there, you do multi-antenna signal processing to try to really boost the reliability of the transmission and boost the data rate. And how do we model? When we model the systems and we try to design new communication strategies, actually the presence of multiple antennas leads to actually the use of chi-square random variables. So you can have, this is the simpler form of chi-square. You can have more complicated form where you have the sum of the square of a normal random variable, but you have the sum over multiple of them. So you can have z square, z1 square plus z2 square plus z3 square, for instance, and all those z's actually all normal random variables. And so all those corresponds to essentially the propagation you have between a given transmit antenna and a given receive antenna. And this is where actually the chi-square distribution comes in. Again, this is well beyond the scope of the course, but if you take fourth-year course on comms, you will see that. Good, so one more distribution that is also used a lot, and again is used a lot in communication, is log normal. Right, so what is this? I have x is normal distributed with a mean mu and a variance sigma square. And what I'm looking at is exponential of x. Exponential of x. So we say that y is log normal because the logarithm of y is equal to x and is normal distributed. Right? So a random variable is log normal distributed when essentially when you take the logarithm of that random variable, the logarithm of that random variable is normal distributed. Okay? So y is log normal distributed because the logarithm of y is actually normal distributed. So same as before, what is the PDF of y? Well, we can start with the CDF, same as what I have done before. And what do we have here? If the exponential here is always positive, so if y is negative, you get something that is 0. If y is positive, what you get is essentially the probability of e of x being smaller or equal to y, which is the probability of x being smaller than the logarithm of y. Right, and this is the CDF of x evaluated at ln of y. Right, so same as before. How do we get the PDF? We take the derivative with respect to y of the CDF. And so what we have here is you take the derivative of that function. You're going to have the PDF of x evaluated at ln of y multiplied by the derivative of ln of y is 1 over y. And this is, again, if y is positive. If y is negative, you get 0. And so what does this give you is 1 over y. Now, this is the PDF of a normal random variable, so it's 1 over 2 pi sigma square e minus x minus mu square over 2 sigma square. And so what we have here is 1 over 2 pi sigma square e minus what is x now is replaced by ln of y. So I have ln of y minus mu square over 2 sigma square. This is for y positive, and y negative, you get this. Okay? Right, so I have done the same trick multiple times today, and I repeat it. Really, you start with the PDF, the CDF of the new random variable you're looking at. You write this as a function of the CDF of the random variable for which you know the PDF. Then you take the derivative, and this is where you get the PDF of the new random variable, right? And so you see this is not normal distributed. You still have something that looks like normal. You have a ln of y, and you have 1 over y. Okay, so where is that used? Well, if I take again this communication, you're going to see a lot of communication. The noise is here, right? This is normal. Where is the log normal is when you have a city like London, you have, when you transmit, you broadcast radio waves, actually those radio waves are blocked by buildings. And so experimentally, what has been shown is that this blockage of the radio wave through a building can be modeled using log normal random variable. So when you model the propagation between a transmitter and a receiver in wireless communication, you use log normal distribution to model this blockage. You can use this chi-square random variable when you have multiple antennas. you use the exponential random variable to model this fluctuation of the received power, together with the noise that is normal distributed. At the transmitter, you have here signals actually also normal distributed. You will see this later on in communication if you take information theory. And then here you have packets of arrival that actually Poisson distributed, right? So if you want to really model and understand the entire system, actually you'll see that all those different distributions will come in different modules. In information theory, you have this a lot, or in communication in general. If you do traffic theory, communication theory, you will see those Poisson here. You do wireless comm, you will have this. And anywhere in communication, you will have this node that is normal distributed. And all those distributions come into play in the analysis of the performance of the systems and how to design a communication strategy to make it reliable to all this kind of randomness that you can have in the system. Okay? Good. So with this, we are almost done for this part. But there's one more thing I want to highlight, is that so far we have looked at specific distribution, and we have computed certain probability assuming a random variable has a certain distribution, right? So, for instance, if I have a random variable with a mean mu, and I know the distribution fx of x, I can, for instance, compute the probability that x is smaller than mu minus a, and the probability that x is larger than mu plus a, right? So this can be computed, is the probability integral of f of x for all the x smaller than mu minus a and all the x larger than mu plus a. The question we try to answer here using what is called Chebyshev inequality is trying to identify what is the actually area under this curve, what is this probability when you don't know the PDF. You don't know the PDF, you don't know f of x. The only things that you know is that you have a mean that is expectation of x, and you have a variance that is given by sigma squared. So you may know the mean and the variance, but you do not know the exact distribution. You don't know whether actually it's normal distributed, it's exponentially distributed, it's uniform distributed, but you still want to say something about this area. Right, so what Chebyshev inequality says is actually you can always upper bound this quantity by the following. If I take any values of a here, this value here that is positive, I can write that the probability of having x minus mu, and I take the absolute value here, being larger than a, which is actually this area that I have drawn here, this is always smaller than sigma squared over a squared. So what that means is that if you take a larger, you're moving those two boundaries further away here, that probability will decrease. That area will decrease. If sigma squared increases, and you fixed a, so you fix those values of a, but you increase sigma squared, that distribution becomes more flatter, right? So the deviation around its means increases, and so that probability potentially can be larger, right? What this tells you is that whatever the distribution of x, right, if you have a mean mu and a variance sigma squared, this probability, so this area here, will always be bounded by this quantity, right? If you know f of x exactly, then you will find a value that is smaller than that, but this is an upper bound on this probability, right? So this is useful in case where you don't know x, you don't know what's the distribution, but you may know its mean and its variance. But you can write this equivalently by saying a is positive, and I'm looking at the probability of x minus mu smaller than a, and now this would be larger. I'm looking at this area here in the white part here is 1 minus sigma squared over a squared. So this is just a complement. So this is a useful inequality. This is valid for all PDF. But you have a slightly more general version of this that says the following. If you have, I will remove the mu here, and I will say if I have any b for all b, and I have all a positive, what I can write here is the probability of having x minus, and I replace mu by b, larger than a, this is smaller than the expectation of x minus b squared divided by a squared. And so what you see here is that if you take b equal to mu, essentially this quantity will become the variance of x, and it boils down to this, right? So you get this expression if you take b is equal to mu. Okay, so this is slightly more general version of this Chebyshev inequality. And the idea is the same. You can compute this probability, but you can try to upper bound it by this quantity, and this would hold for any probability density function. Right, so we can use this in a few cases just to understand a little bit what it does. So imagine I have expectation of x is indeed mu, but I have the variance of x is 0. If the variance of x is 0, so what does that mean? I can write p of x minus mu here, being larger than a, is smaller than 0 for all a positive. Right, so for all values of a positive, it can be as small as you want. The probability, you take a as small as you want, so you take this, you move it there, and the probability of having this area here equal, this probability will be always upper bounded by 0, even if you take a as small as you want. So what that means, in other words, is that the probability of having x equal to mu is equal to 1, because that holds for all a. So this means that if the variance is equal to 0, whatever the probability density function, if the variance is equal to 0, it means actually you don't have really random variables anymore. You say that actually x will be equal to mu with probability 1, right? I'm not sure it's very interesting in practice, but this is essentially what you get if you take the variance equal to 0. If you take something similar, but if you say expectation of x squared is equal to 0, so I'm just saying that expectation of x squared is equal to 0. Now, we know that the variance of x is expectation of x squared minus the square of the expectation, right? And this is positive or equal to 0. Right? So because this is positive or equal to 0, and this is equal to 0, this term is equal to 0, that means that expectation of x has to be equal to 0. And that means that because this is equal to 0 and this is equal to 0, the variance of x equal to 0. And so if mu is equal to 0 and the variance is equal to 0, from here you can say that the probability of x equal to 0 is equal to 1. Right? So in that case, that random variable x is actually, with probability 1, is equal to 0. One more thing, if I write a as k sigma, where sigma is my standard deviation, I can write this relationship that we have here slightly differently, where a is now k sigma, and I can plug this into this expression. So what I have is the probability of x minus mu being smaller than k sigma is larger than 1 minus sigma square over k square sigma square, right? So I'm just using this relationship here where I replace a by k sigma, right? So what you get here, what that means is that for all a positive, or for all k, because here a is equal to k sigma, so for all k, or any values of k, the probability of having x being between mu minus k sigma and mu plus k sigma is larger than 1 minus 1 over k squared. Right, so imagine you take k is equal to 3. If k is equal to 3, that means that the probability of having a random variable x between its mean minus 3 sigma and its mean plus 3 sigma, this is always larger than 1 minus 1 over 9, which is 8 over 9. Right? Whatever the distribution x, if you take x, the probability that x is in between those two boundaries is larger than 8 over 9. So if I have the mu is here, and I'm looking at mu minus 3 sigma and mu plus 3 sigma, and I have a certain probability, I don't know what it is, this probability here, this area, will be always larger than 8 over 9. Right? If you know the exact probability, it will be maybe probably larger than this. And we have seen an example, right? When we had mu equal to 0, and we said that x was normal distributed, and you take sigma here is actually 1, so you had a standard normal random variable. What we did just earlier on, we had this, right? We looked at the probability that z is between minus 3 and 3, and we showed that actually this is 0.99, right? So what you see here is that this holds when z is normal distributed, standard normal. But actually what you see here, actually this holds for any x, any PDF of x, but this is a lower bound. So here you get 8 over 9, and here we had 0.99. So it's indeed larger than that, but maybe for some distribution it will be lower, it will be closer to 8 over 9. For the normal random variable, it happens to be larger and close to 1, right? So what's the usefulness of this is really to be able to say something about this probability when you don't know anything about x. You may know maybe the mu and the variance, but you don't know what's the actual distribution. You don't know whether it's exponential, Gaussian, normal, or whatever. Okay? So let me continue a bit for 5 minutes. So with this here, we actually done with the first part of the second part of the module. Right, so we had this somewhere. Right, so we had part 2. Actually, we done with one random variable. We looked at the discrete and continuous. What I can start doing now is looking at system and reliability, system and components reliability. You see, this part is not complicated. It's just an application of things that we have done so far. So it will not take much time. But depending on what you do in the future, sometimes actually those notions actually something that actually are used. So very often in a system, you want to look at some form of reliability. So you model a system as something like where you have an input and you have an output. And the system is made of multiple components, right? For instance, here I have a component here, a component there, component there, component there. And I'm saying that actually the system functions, so the system functions properly if there is a path. So if there is a path, a functioning path between the input and the output. And what I want to see and compute is the probability actually the system functions. So here is a combination of having actually components actually in series and in parallel. So the first scenario we can look at is what you have only series. So you have component like this, they're only in series. You have a component C1, C2, all the way to Cn. This is your input. This is the output. And when I write C1 or Ci, it means actually the component or the system Ci actually fails. When I write Ci, the complement of Ci, it means actually the component Ci's functions, right? And this can happen with a certain probability. So the probability of Ci functioning can be called theta, and Ci non-functioning is called 1 minus theta. And what I have here is different components, C1 all the way to Cn. They're all identical, and they all behave independently from each other. Independently. Right, so how can we compute the probability that the system functions? Well, this is something that we have done. It's actually just writing this using union or intersection. What is the probability that the system function? The probability the system function is, because they're in series, it functions whenever C1 functions and C2 functions all the way to Cn, right? So that's the probability that C1 functions and C2 functions all the way to Cn functions, right? Now I'm saying they're all independent, right? So that's the probability of having C1 functioning multiplied by probability of C2 functioning all the way to probability of Cn functioning. And what is the probability that actually this functions? This is 1 minus theta. This is 1 minus theta. This is 1 minus theta. So what you get is 1 minus theta to the n. Okay? That's direct application of what we have done before. I'm using here the independence. So independence, and we have seen this, the probability of intersection is the product of the probability when they're independent. And here I'm using the fact that they're identical. Right, so because they're identical, all those probabilities are actually the same. Good, so what if now I have systems in parallel? So I have those components, but now I have an input and an output. And I have components in parallel. I have C1, I have C2, all the way to Cn. Right, so what's the probability the system functions? Well, it's different from here. The system functions when at least one of them functions, right? So I need to have at least one of those paths functioning. So there's a probability that C1 functions or C2 functions. So I have a union, I don't have an intersection, all the way to Cn functions. Now, this is something we have done before. You can write this as an intersection of C1, C2, all the way to Cn, and I take the complement of the intersection. So the union of the complement is equal to the complement of the intersection, right? Remember this? We did this a few weeks ago. The probability of the complement, this is 1 minus the probability of this event, C1, C2, all the way to Cn, right? You remember? P of A naught is 1 minus P of A. Now this is 1 minus, I have the probability of the intersection. This is P of C1, P of C2. They're all independent. P of Cn, right? This is the independence. This is P of C1 is here, is theta. So this is 1 minus theta n. And I'm using here the fact that actually they are identical. Right? Okay, so with this, you get actually two building blocks when the systems are actually in series or in parallel. And from there, what you can do, you can build actually the probability of the system function when you have a combination of series and parallel. Right? So if you have a combination of series and parallel, so what do we have? Let's say you have an example here. You have an input. You have an output. And I have now here a case where I have two branches. And on each branch, I have multiple components here. So I have C1, C2, C3, C4, C5. Right? So how can I model the probability that the system function? Well, I can use what I have done before. What I can do first, I can abstract this. So this is equivalent to having an input, an output, and I have only two branches. And I have a branch S1 and a branch S2. Right? Where S1, so I abstract those three here as just one system, S1, where S1 means branch 1 fails. S2 means branch 2 fails. Right? So what's the probability that the system functions? Is the probability that either S1 works or S2 works. So I have either S1 working or S2 working. Right? So either S1, either this branch works or this branch works. This is the probability of having S1 intersection S2. The complement, this is 1 minus the probability of S1 intersection S2. And I'm doing exactly what I did earlier on. Because the components are all independent, this is 1 minus the probability of having S1 multiplied by the probability of having S2. And so what I'm left with is to compute the probability of having S1 and the probability of having S2. Right? So how can we do this? Well, we can reuse what we have done here. Right? S1, the probability that actually S1, the probability that S1 occurs, so actually the probability that S1 fails is 1 minus the probability that S1 works. And what is this quantity? Is what we have done here, right? Is the probability that system function when you have series element. This is 1 minus this quantity, 1 minus theta, and you have 3 elements in this case for branch 1. So you have 3. PS2, 1 minus of not S2 is 1 minus theta square because you have 2 elements. So if you take those 2 values, you plug into here, you plug into there, then you get the probability that the system functions when you have a combination of series and parallel. Okay? So you will see this, you will play with this in the classes as well with Bernie. This is called reliability, but essentially it's a direct application of what we have done earlier on in the course. Okay, so we'll stop here for today, and I see you next Friday for some more stuff. Thank you.